This video, we're going to do the last problem of section 1.3, approximations and limiting cases. 1.16, projectile with drag. Consider a projectile subject to a drag force of F equals m negative m alpha v. If it is fired with speed v naught at an angle of theta, it can be shown that the height as a function of time is given by y of t is equal to 1 over alpha times v naught sine theta plus g over alpha times 1 minus e to the negative alpha t minus gt over alpha. Show that this reduces to the usual projectile expression y of t is equal to v0 sine theta t minus gt squared over 2 in the limit of small alpha. What exactly is meant by small alpha? So when we're first analyzing our equation, we see that there is an e to the negative alpha t. What this really means for our small alpha is that alpha t has to be much less than 1. 1 is often the kind of quantity or like value that we set. Mathematically, we can also write this as the limit as alpha goes to 0. And because of this, we can use a Taylor expansion centered around 0 that approximates basically small alpha, or alpha close to 0. So e to the x in Taylor expansion and for sigma notation, it's the summation n equals 0 to infinity of negative 1 to the power of n times x to the n over n factorial. And our x in this case is negative alpha t. So let's just write that. Well, I'm going to write I wrote the first 4 terms and it just keeps going on. So 1 minus alpha t plus alpha t squared over 2 minus alpha t cubed over 6. And this 2 is 2 times 1, 6 is 3 times 2 times 1, plus an infinite amount of numbers, right? Now we have 1 minus e to the negative alpha t, right? Because that's what's in our equation. And for that, we can just take out the 1, right? And now let's just plug this back in. So we have all the other ones, but let's just focus on the whole part of this 1 over alpha times our quantity. Now let's just recognize that we have an alpha in every single term of our expansion now of 1 minus e to the negative alpha t. So we can essentially cross these out, right? So then what happens is that we get y of t is equal to v naught sine theta minus gt times t minus alpha t squared over 2 plus alpha times t squared over 2 plus alpha squared t cubed over 6, and then it'll just keep going. So basically all that's happening is that instead of having alpha to the n, t to the n, we have alpha to the n minus 1 times t to the n, right? Okay, so now our key that is harder to see for this is we're gonna expand this v naught sine theta minus gt times the Taylor expansion revised. So what happens is we get this humongous equation, but the only things that really matter is that we get a gt over alpha, right? And then that will take out this minus gt over alpha we have here. And then we have to recognize now that it's the limit as alpha goes to 0, right? So basically when we take these limits mathematically, if applicable, you can just plug in 0. So now we see that we basically only have 2 terms without alpha, which is v naught sine theta t and then the negative half gt squared. And then we also have no alphas in the bottom. Alphas in the bottom would be bad, right? Because if you have them in the denominator, then it'll just blow up to infinity and then this doesn't work. But we cross out the all the gt over alphas and then there's no more left, so we're clear for that. And all the other terms except the 2 that I mentioned before all have alphas, so those as the limit as alpha goes to 0, those will also go to 0 basically, so we can just take those out. So then we get that y of t is equal to v naught sine theta t minus 1/2 gt squared. Yay!